All right, so when we're working with differential equations, we're generally, at least at the beginning, working with problems where we have some initial conditions. So we may have our original function defined at a particular point in time, and then we may have the derivative also defined at that same point in time. But sometimes things can be more complicated. We may not have information on the derivative. We may have only information on the original function. And then it's no longer an initial value problem. We may have information only about the derivative and not about the original function, or we may have information about the original function and the derivative, but at different points on the function. And so now we begin to be talking about boundary value problems and not initial value problems. And boundary value problems can have their own sort of unique set of issues. And we want to walk through some methods for solving those problems so that we don't only end up with trivial solutions. Now, the concept that we're going to be working with here are eigenvalues and eigenfunctions. And you may be thinking, eigenvalues and eigenvectors. I may have done those in linear algebra, but these are related concepts, but now we're working with functions as our vectors. So they're going to give us characteristic functions for a particular problem solution and not characteristic vectors. But a lot of the concepts are the same. So if you've encountered eigenvalues and eigenfunctions in linear algebra, then you will see some connections between these concepts. However, if you have not done linear algebra, that's okay. We're going to walk through all of the algebra that you need in order to pull this off. Now, the form of our solution, when we have boundary value problems, can sometimes, if we're not being very careful, can sometimes produce solutions that appear like they're going to be zero everywhere. And those are perfectly valid solutions, but there may not be the only solutions. We may be missing solutions by only considering the trivial case. So sometimes we will have second order equations that have unknown coefficients in them. And so we may be interested in finding out for certain values of that unknown coefficient, what are the characteristics of that solution? How is it going to behave more abstractly? And so we're going to have to be dealing with problems that have these essentially unknown values in them. And then we may have to look at more than one possible case for what if the value is this, then what happens? What if the value is that, then what happens? And so forth. And so sometimes we may get trivial solutions like y equals 0. And in other cases, we may get much more interesting solutions, but which are maybe infinite in number and maybe a little bit more difficult to pin down. But at least we can get a general behavior for those functions. So let's look at an example of what we're talking about here. So here we have a differential equation. The second order. It has no middle term, so it's y double prime plus lambda y equals 0. And we have this unknown coefficient in here. It's not 4. It's not something that we know about. It's just some unknown value. And then moreover, we have this boundary value condition, not an initial condition. We know what the function is doing at 0, and then we know what it is doing at some other fixed point on the function. We know that it's also 0 there. So we're going to begin by writing the differential equation as its characteristic equation. So we're making the same initial assumption that we would for any other second order equation of this type. Any homogeneous solution, we're going to assume that we have a y equals e to the rt as our function, and with some unknown coefficient. And when we solve for the characteristic equation, we take the derivatives, we factor out the e to the rt. All of that other algebra remains the same. So you can think of replacing y double prime with your r squared, and y with just the constant, and you end up with this. So the characteristic equation turns out to be r squared plus lambda. And if we solve for that, r squared is equal to negative lambda. So this is going to suggest, in theory, three possible solutions. So if lambda is negative, then negative lambda will be positive, and so the characteristic equation will have two positive, real, and distinct roots. If lambda is positive, then the right side of the equation will be negative, and that will produce purely imaginary roots. And if lambda is 0, then r is 0, and this is a repeated root. And each one of these cases will have to be analyzed separately. So let's consider case 1. So we'll start with the lambda equals 0 case, since that's the simplest case. If you replace lambda equals 0 in the original equation, you just get y double prime is 0. And again, back in the original differential equation, then that will give you solutions that are constants and linear functions. And so y will take the form ax plus b. And then we can look at the boundary conditions to see if we can match this. So if we plug in y of 0 is 0, then we get b to be 0. And if we test a value for our L, in this case, we were very generic, but it doesn't really matter what the exact value is. If we plug in pi for L, then we're going to get 0 times a times pi. 0 is equal to a times pi. But even if we weren't using pi, any value of L would also make this require a to be 0. And so when lambda is 0, we're left with just the trivial solution. The only way that we can get a straight line to go through 0 twice is to make the whole line 0. So this is, again, a valid solution, but it's boring. So let's consider the case where lambda is negative. So to ensure that lambda is negative, we're going to define lambda to be negative mu squared. Now, mu squared is positive because if you take any real number and you square it, it's a positive number. And so I'm putting a negative in front of a squared term. You're insisting that it be negative. So again, we're trying to ensure that lambda is always negative. We make this substitution. In this case, we can do it into our characteristic equation. And when we do that, we get that r squared is equal to mu squared, or that r is equal to plus and minus mu. Now, that means that there's two possible solutions. R is equal to mu, and r is equal to negative mu. And there's two ways that you can write solutions like this. So you can write them as the base exponential functions, a e to the mu x and b e to the negative mu x. Or depending on your professor, they may be enthralled with hyperbolic trig functions, in which case this is also a valid way to express the solution to the equation as hyperbolic cosine mu x and hyperbolic sine mu x. These are algebraically equivalent expressions of each other, so which version you prefer is entirely up to you. For the sake of the example, I'm going to use the second equation here, because the algebra turns out to be a little bit easier, but you will get the same result if you use the other set of solutions. So if we substitute y of 0 into this function, then hyperbolic sine of 0 is 0, hyperbolic cosine of 0 is 1, and so that forces the constant c to be 0. Now, that leaves us with this, and then we plug in our L value into our hyperbolic sine function. The only place hyperbolic sine is 0 is actually 0. And so since this function, the hyperbolic sine, cannot be 0, that forces d to be 0 as well. And again, that leaves us with only the trivial solution. And we have a similar thing going on with the the exponential version of the equation, neither the exponentials can be zero, and so that forces the coefficients to be zero, and we're back to the trivial solution. Now, in case 3, we're going to assume lambda is positive. Now, if lambda stays positive, we can set lambda equal to mu squared, not negative mu squared, positive mu squared. So since mu can be anything, but mu squared will always be positive, this ensures that lambda will be positive. So we can plug this into our characteristic equation, and we get r squared is equal to negative mu squared. That means that our solution to this is pure imaginary, plus and minus mu I. And then when we plug that into our solutions, the imaginary solutions become sine and cosine functions, A cosine mu t and B sine mu t. Now, if we plug in our initial boundary conditions, then y of 0, again, sine of 0 is 0, but cosine of 0 is 1. That means A must be 0. And then if we plug in the second condition, then we get this expression. Now, it might initially seem like this will also force B to be 0, which is certainly a possibility. However, it is also possible to make sine of mu L equal to 0 for some values of L. Or more to the point, some values of mu. Since we're looking for the values of mu that are going to make this non-zero, so this entire solution non-zero. So sine of mu L will be equal to 0 when mu L is equal to some integer multiple of pi. So pi, 2 pi, 3 pi, negative 2 pi, 0, etc. So if we set this condition, we can then solve for mu in terms of L and N and pi. And so what we end up with is that mu is equal to n pi over L, and therefore lambda is n squared pi squared over L squared. And so in this case, we will actually get a non-zero solution. We won't be able to solve for this missing constant, but we will see that our solution can satisfy this equation for certain values of lambda. And when those values of lambda are satisfied, then you will get a sine wave out of our solution. Now, let's look at a second example, and we'll go through the same steps. This one is a little bit more complicated, but fundamentally, the same idea is at play. So we're going to find the eigenvalues and eigenfunctions for the boundary value problem, y double prime plus 4y prime plus lambda y equals 0. And we have the same boundary conditions we had before. So when we set up our characteristic equation, r squared plus 4r plus lambda equals 0, we're going to use the quadratic formula to solve for r. And when we use the quadratic formula, we end up getting -2 plus and minus the square root of 4 minus lambda. So this is going to give us 3 cases. So case 1 will be 4 minus lambda is positive. Case 2 will be 4 minus lambda is 0. And case 3 will be 4 minus lambda is less than 0, so negative. Now, in the positive case, again, we're going to replace, in this case, 4 minus lambda with mu. And then our r is going to be -2 plus and minus mu. These are 2 real solutions since we specified that lambda was mu squared. And that a solution to the differential equation will have this form. And again, alternatively, you can use the plus and minus mu components that are different from the 2 problems to be caution cinch. If we plug in our initial conditions, then the 0 here will make this all of 1. cosh of 0 is 1, sinh of 0 is 0, and that's going to imply that a is 0. And then if we plug in our L value and set that equal to 0, then this exponential part for any value of L is never going to be 0. And sinh is also never going to be 0. And we're left, as with the previous example, with the trivial solution. Now, again, similarly, case 2, this is the case where we have the equal to 0. So we're going to set lambda equal to 4. And that's going to leave us with the repeated root, -2. And then our solution will have this form. And again, we can test our initial conditions. And when we do that, we are again algebraically forced to conclude that both A and B are 0, and therefore we have only the trivial solution again. And then, of course, in case 3, then we're going to set, again, similarly, our condition that must be negative, we're going to set 4 minus lambda equal to negative mu squared. And then when we plug that into our characteristic equation, we're going to get -2 plus and minus mu I. Our complex solution, we have the E on the outside, and then A cosine mu x and B sine mu x for the imaginary pieces. And then when we plug in our initial conditions for the 0, the exponential will be 1, sine of 0 is 0, cosine of 0 is 1. That forces A to be 0. And then the second one, again, the exponential part can never be 0, but it's, as far as the sign goes, it's just a constant at this point. And then we again are left with this position where we're trying to force sine mu L to be 0, and our choices are to let B equal to 0 and get the trivial solution, or to find a condition on mu that will force sine mu L to be 0. And so similarly to the last example, this expression will be 0 when mu L is equal to multiples of pi, integer multiples of pi. And again, we solve for mu, and then mu was equal to 4 minus lambda. And so then from here, we can solve for lambda, and we get 4 minus n squared pi squared over L squared. So these are our eigenvalues for the differential equation, and the eigenfunction is sine mu x.